The four fundamental kinematic equations from all the way back in 1D kinematics, they apply for stuff moving in a circle. For example, we have x being displacement. Well, now we have angular displacement. We had linear velocity become angular velocity. Linear acceleration, angular acceleration, which we looked at last video. And the kinematic equations, for example, this classic one, we can rewrite it as this. Angular velocity instead of normal velocity, angular acceleration instead of normal acceleration, and we get the same equation, but now it's in terms of rotation. And remember, the kinematic equations only apply when acceleration is constant. So that means all angular acceleration we'll be looking at today is average. Let's go through a problem. Imagine you're in a biotech lab and you're doing some science research, and you have this machine, and your machine spins test tubes in a circle. It's called a centrifuge. So here's the circle, and it starts from rest, and then after 30 seconds, it reaches full speed. At full speed, it's moving 20,000 spins per minute. Let's find two things. As an engineer working at this biotech lab, you're tracking two things. One, how fast it was speeding up. So that would be average angular acceleration. And two, how many spins happened during these 30 seconds. Now we need to know the right formulas to use. And for that exact purpose, for this big chunky topic, I made a cheat sheet for it. It's free in the description. If you haven't grabbed it yet, it's gonna help you a lot. Let's solve question one. So we're looking for average angular acceleration. If you remember, the formula we looked at last video was change in angular velocity divided by change in time. Okay, pretty straightforward. But what is the angular velocity? It's 20,000 spins per minute. But spins per minute isn't really a unit we use in physics. We want radians. So if there's 20,000 revolutions per minute, let's divide it by 60. We have 333.33 spins every second. And to turn your spins into radians, all you have to do is multiply by 2 pi. You get this number, 2094 radians per second. Guess what this is? This is our angular velocity. If we plug this in here, and for time, it takes 30 seconds, right, to reach this velocity. So that would be 2000 radians per second divided by 30 seconds. You get angular acceleration as 69.8 radians per second squared. That's how we find problem one. How about number two, which is asking how many spins it did during the speed up phase. Let's use a kinematic equation. Let's look at what we're given and what we're looking for. What are we given? Time is 30 seconds. Initial angular velocity was 0. Final angular velocity was 2094 radians per second, as we just found. The average angular acceleration we just found was 69.8 radians per second squared. And the angular displacement, we don't know. Since we're looking for how many spins it did, angular displacement would be what we're looking for. So let's find a formula that connects all of these together. There's a perfect kinematic equation for this, which is this. Displacement equals initial velocity times time plus 1 over 2 acceleration times squared. Of course, normally it looks something like this, but we're doing rotation here. So we put in our angular quantities instead of linear symbols. Let's do some plugging. Since initial velocity is 0, this term is just gone. What's angular velocity? Angular acceleration is 69.8 and time is 30. We multiply this by 1 over 2 to find 31,410 radians. Okay, but the problem is it's in radians. What is this value in revolutions? To do that, we divide it by 2 pi. And this gives us roughly 5,000 full spins. So in the 30 seconds it took to speed up to its maximum velocity, it spun 5,000 times. By the way, something that really helps me is having all the formulas you ever need in one place. And I make these cheat sheets for myself, and if you want your own, it's in the description for free. So go sign up.